a picture of a little refraction taking place here again, guys. We've got a boundary between two materials. We're going to make this one, let's say, air, and let's make this one glass. Air has an index of refraction of about 1.0, not exactly, but it's pretty close. Glass has an index of refraction of about 1.5, although it does depend a little bit upon the type of glass that you have. Let's say that we've got a ray of light going from the first medium towards the second medium. In other words, going from air to glass, which of course happens all the time, right? Light's going from air to glass right here, literally in this room, as the light's traveling toward the window there. What happens to this angle of incidence when the light strikes the glass? In other words, is the angle of refraction going to be less than the angle of incidence or bigger than the angle of incidence? Smaller than theta 1 or bigger than theta 1? Think it's going to be bigger? What happens when light goes from air to glass? Does the wave speed up or does it slow down when that happens? It's going to slow down, right? It's going to slow down. When you go from a low to a high index of refraction, it slows down. As light slows down, there's a couple of other things that change as well. One thing doesn't. Frequency stays the same, right? But there's a couple of other things that change as well. One of them is the wavelength. One of them is the angle. When the speed decreases, what's going to happen to the wavelength? When the speed goes down, the wavelength goes down as well. If the speed decreases, the wavelength decreases. So here we're going from a low to a high index of refraction. The speed decreases, the wavelength decreases. What about the angle again? Well, the angle decreases as well. Theta 2 will be smaller than theta 1, right? Theta, lambda, and V kind of go together. As one increases, the other will increase. As one decreases, the other will decrease. Index of refraction goes the opposite way. If we're going from a high speed to a low speed, that means we're going from a low index to a high index of refraction. All right, let's draw another one here now. Let's say we've got another ray of light right here with a really, really big angle of incidence right here, big theta 1. Obviously a lot bigger than we had for our first theta 1. How is theta 2 going to compare to theta 1 in this case? It's not going to reflect, no? Is it ever going to reflect there? Could it reflect? No? No, it can't. What's going to happen to theta 2? Here we said theta 2 is smaller than theta 1. What about theta 2 down here? It's still going to be smaller than theta 1. Now, it's going to be bigger than the theta 2 that we have drawn first, bigger than the green one, but it's still going to be smaller than the theta 1. Therefore, if it's smaller than the theta 1, it can't reflect. You will never get total internal reflection when you're going from a low to a high index of refraction because theta 2 is always smaller than theta 1. In order to get reflection taking place, theta 2 has to be 90 degrees. You can't have an angle that's 90 degrees for theta 2 if it's always smaller than theta 1 because you can't have an angle of incidence bigger than 90. Does that make sense? Because it bends toward the normal line, because theta 2 is always smaller than theta 1, you're never going to get reflection taking place. Now, if we flip that around and we go from glass to air, then it is possible to get reflection taking place. How come? Well, let's look at that first ray again. Theta 1 represents the angle of incidence of that first ray. And because it's going from a high to a low index of refraction, what's happening to the speed? It's speeding up, right? As it speeds up, as V gets bigger, lambda gets bigger. Theta gets bigger. So theta 2 is going to be bigger than theta 1 in this case. Now, we still don't have reflection taking place, but if I increase the angle of incidence to a great enough point, theta 1 will produce an angle of theta 2 that's still bigger, and that theta 2 may, in this case, actually be 90 degrees. In other words, that ray of light may actually skip along the boundary between the two materials. That's when total internal reflection begins to occur. What's the other name we give for theta 1 now that reflection has begun to occur? The critical angle. We're going to call theta 1 theta C now, the critical angle at which reflection begins to occur. Anything above that, any angle above that, right, it's going to just reflect, and no refraction is going to take place at all. So how do we find the critical angle? I'll take a look at the picture here. What's the angle of refraction, theta 2, when total internal reflection begins to occur. In other words, what's the angle of refraction when the critical angle has been met? Every time. What is it? 90 degrees. Yeah, so if we want to find theta c, we're going to set theta 2 equal to 90 degrees. And then we're going to use Snell's law, just like we have for a number of other problems. It becomes sine theta 1 over sine theta 2 equals n2 over n1. Theta 2 would be 90 degrees, and theta 1 would be the critical angle. So it becomes sine theta c over sine 90 degrees is equal to n2 over n1. Now, good news here, a couple pieces of good news. Number one is that sine 90 is 1. So whenever you're doing a critical angle problem, you can always just drop this if you want, because the bottom number is always going to work out to be 1, if it's a critical angle problem. The second thing is that if you mix these up and punch them into your calculator backwards, what's going to happen, Victoria? I think it was you yesterday that had that issue. You're going to get an error on your calculator. What does that tell you? These are all mathematically possible to do. If you get an error on your calculator, you've done something wrong. The good news is here, if you mix up N2 and N1, which is a fairly common mistake to do, your calculator will tell you that you've messed it up because you're going to get an error. If you get an error on the calculator in this question, then flip them around because that's almost certainly the mistake that you've made. Right? Then, of course, you solve for theta 1 or theta c, and you're good to go. We had a couple of questions that I asked you to work on yesterday. And to finish up for today, the critical angles of the following interfaces: water and air, diamond and air, and diamond and water. How many people got these done, first of all? Okay. They don't tell us which way we're going here. Is it water to air or air to water? How do we know? How do we know it's water to air and not air to water? Huh? Yeah. Check that table that you saw in your notes a while ago. You know that the index of refraction of water is higher than air, and if it is, it's got to be going from water to air. Renee, is that what you're going to say? The other way you can look at it is, usually if they have an interface that's going from air to water, they'll usually say an air-water interface instead of a water-air interface. Okay, but let's not take that as a for sure thing. Let's look at what you guys were saying and use that as a for sure thing. If you're going from a high to a low index of refraction, we're going from water to air. But again, if you mess that up, Victoria, what's going to happen? You're going to get an error on your calculator. Okay? All right, let's do all three of these actually. Okay, they should go fairly quickly for us. The critical angle between water and air. So we're going to say for question number A, or question A, sine theta c is equal to n2 over n1. Where did the sine theta 2 go? Where did that disappear to? It's equal to 1, right? Sine theta 2 is sine 90, which is 1. So if I want, I can just drop that. I don't have to, but I can. Theta c becomes equal to the inverse sine of n2 over n1. When we do the math on that one, the inverse sine, by the way, what is the index of refraction of air? I think it's 1.00. What is it for water? 1.33. We should get an angle there of 48.8 degrees. That's a fairly high critical angle. Light can reflect off of the boundary between water and air, but it's got to be at a fairly high angle in order to do that, at least 48.8 degrees. Now let's take a look at the interface between diamond and air. We use the same equation. Theta c is equal to the inverse sine, this time of 1.00 over 2.42. When I do that angle, I end up getting 24.4 degrees, which is a dramatically lower critical angle. In fact, exactly half of the critical angle between water and air. Finally, the third one, diamond and water. Theta c is equal to the inverse sine. We know we're going from diamond to water, high to low index of refraction. This one is going to be 1.33 over 2.42. When I do the math on that one, I should get 33.3 degrees. Take a look at all three of these angles. Water and air has an index of refraction ratio of 1 to 1.33. Diamond and air it's actually more, 1.33 to 1, I guess, isn't it? This one is 2.42 to 1. And this one is 2.42 to 1.33. Which one would you expect when you read the question before you look at any answers or solve for anything? Which one would you expect to have the smallest critical angle? Diamond and water? How come? Okay, want to change your mind? Okay, good guess. Not right, but a good guess. Yeah. Why water and air? Yeah. Well, you're exactly opposite, actually. We're looking for the smallest critical angle. The one with the smallest critical angle is going to have the biggest difference in index of refraction. Does that make sense? The one with the biggest critical angle is going to have the smallest difference in index of refraction. Here's how I remember that. Okay, I remember it specifically using the diamond example. Okay, there's nothing that I can think of that has a smaller critical angle than diamond to air. Well, diamond and air have the biggest difference in index of refraction of any two things that I can think of. So those two things have the biggest difference in index of refraction, yet the smallest critical angle. That's how I remember, personally, that a big difference in index of refraction gives us a small critical angle. It allows total internal reflection to happen easier. If you can't remember that, then figure it out. Do a couple examples and figure it out. Okay? Your homework tonight, after we finished going over this refraction stuff, this total internal reflection stuff, the homework tonight is worksheet number 17. Which is more of the same stuff. It kind of goes back to Snell's law, not all total internal reflection, but there is, I believe, a couple total internal reflection questions toward the end of that worksheet. So let's get that done for tomorrow, please. And we're going to move on to something a little bit new. Today we're going to take this refraction thing a step further, just like a week ago we took the reflections thing a step further. Okay, we went from plane mirrors to convex and concave mirrors. Now we're going from just plain refraction to curved lenses, which of course use refraction, but use it in a little bit of a different way because we're curving the surface as opposed to a straight flat surface. Two types of lenses, just like there were two types of mirrors, converging lenses and diverging lenses. What do you notice on the board right now that's different than what we saw on the board with mirrors? Yep. Yeah. Good, Shelby. Very good. Converging mirrors were concave mirrors. Converging lenses are convex lenses. Diverging mirrors were convex mirrors. Diverging lenses are concave lenses. What does a convex lens or a converging lens look like? Well, it's the one that's bulged out in the middle. Unlike the converging mirrors, which is the one that was caved in the middle. Okay, it's a magnifying glass, right? A converging lens, a convex lens, is a magnifying glass. A diverging lens, okay, one that's thinner in the middle, a concave lens, the glasses that I have on right now. Okay, look around the room right now, I only see 4 of you with glasses on right now. I suspect that all 4 of you are like me and that you are nearsighted. That means if you take your glasses off and hold a piece of paper in front of your face, you can read that piece of paper. Is that right? No? You can't? So yours are reading glasses? Okay. Most people that are young and middle-aged, like me, if they have trouble with their vision, it's going to be trouble with seeing far away, not trouble with seeing close up. As we get older, most or all of us will need reading glasses. If we live long enough, right? If we live to a ripe old age of 70, 80, 90 years old, we will almost all certainly need reading glasses. They're convex lenses. Right now, those of us who need glasses, it's almost exclusively concave lenses or diverging lenses. And that's because we can usually see nearby. We can't see far off. What happens with people like me is the light comes in, you can see the picture of the eye right there. The light comes in more or less parallel to the principal axis, goes through the convex lens of the eye, and then converges, right? It's a converging lens, but it converges not on the retina back here, it converges in front of the retina. So what do I have to do? I have to stick a lens in front of my eye that compensates for that. I have to stick a lens in front of my eye that spreads the light out. That's what this lens does, is it spreads the light out. And therefore, because it's spread out, goes through the lens of the eye, it's going to converge still, but it's going to converge a little bit further back right on the retina. Now, if you have a little bit of trouble seeing close up and not far off, then you're going to have convex lenses in front of your eye, like the magnifying glass is basically in front of your eye. What your problem is that the rays of light aren't converging in front of the retina. Your rays of light are converging behind the retina, back here. Well, we want them to converge on the retina. So what we have to do in that case is put a convex lens in front of the eye to bring the rays closer together before they enter the lens of your eye. Make them converge a little bit closer, a little bit further up. Make sense? See a picture right here? I put this on last semester. I thought when I saw this, this was the perfect thing to add to this notes. This is a picture that was tweeted by Chris Hadfield. You guys know who Chris Hadfield is, right? Yeah. He was the commander of the International Space Station until, I think it was until February or March of this year. And first Canadian that was the commander of the International Space Station. It was fantastic. He would tweet things and put things on Facebook every day, like pictures of things, and he would share videos of how you would brush your teeth in space, and how you would comb your hair in space, and how you'd go to the bathroom in space, and with no gravity, and so on and so on and so on. Well, one day I remember he tweeted this picture, and as soon as he did that, I copied this picture and put it in these notes. It's perfect. Okay, this is a water droplet that's in front of his eyes, in front of his face. First of all, notice the shape of that water droplet. It's perfectly spherical. It's not the typical shape of a water drop, right? The teardrop shape. Why not? Why is it spherical? This has nothing to do with lenses yet. Why is it perfectly spherical and not teardrop shaped like water droplets would normally be, right? Yeah. There's no gravity to stretch it out. That's what a teardrop is, right? It's a water droplet that's perfectly spherical. It's stretched out because of gravity. Well, here we don't have gravity. We do have gravity, but it's like 0 G's. Okay, we're experiencing no gravity. What I found interesting, though, was not the shape of this droplet, but the image that we see inside. We look through this water droplet, what do you see? His face is upside down. This is a lens, right? When you look in a magnifying glass, what do you see? You see an image that's bigger, and you see an image that is right side up. If you go back from that, okay, if you take your object back from your magnifying glass, okay, it might surprise you what you might see. Just like with mirrors, we can see different images depending upon where the object is relative to the mirror, relative to the lens in this case. Okay, this is a lens. This is a convex lens. The image that we're going to see of Commander Hadfield's face in behind this lens is going to be different depending upon where he is. If he backs up from this water droplet, he's going to appear different than if he's really close to it like he is right now. Okay, does that make sense? What we're going to do today is spend, well, for the next 7 minutes at least, spend a few minutes drawing ray diagrams for convex or converging lenses that will help us to see exactly when we're going to see this image. In other words, when the image is going to be upside down and smaller, and when the image is going to be something different, maybe bigger, maybe real, maybe whatever. Let's take a look at your template now and look up at the board here at the same time. What kind of lens do we have here? Lens. Yeah, it's a converging lens. Another name for a converging lens is a convex. If it was a mirror that was converging, then it wouldn't be convex, it would be concave. It's tough to keep those straight sometimes, okay? It's easy to mix them up. Converging means either convex or concave, depends upon what you have. If it's a mirror, then converging is concave. If it's a lens, then it's going to be convex. All right. There are 3 rays that we can draw for every ray diagram, just like the ones for mirrors. But The good news is, for lenses, we only ever have to draw two, and it's always going to be the same two. The third one is really irrelevant. The first scenario that we're going to draw is when our object is way beyond the focal point, way beyond. This, by the way, it wouldn't be the center of curvature anymore. We just call it 2F, way beyond twice the focal point. The first ray, you can probably predict what it's going to look like. It's going to go from the top of the object parallel to the principal axis. But this time, it isn't going to reflect. It's going to refract. It's going to bend. Where do you think it bends? It's a converging lens. Rays parallel to the principal axis will converge at the focal point. It's going to go down here, right through the lens and right through the focal point. Now, I'm approximating it a little bit with the way that I've drawn it here. Okay, the reality is it doesn't bend once in the middle of the lens. It bends when it gets to the edge, and it bends when it gets to the edge again. So the reality is it would look more like this. Bending once, bending twice. But it's just easier to draw it like this, and we end up getting the same result. So that's my suggestion, is that you do it the same way as I have. Draw your ray to the center of the lens, to the middle of the lens, and then bend it from there. The second ray is a little bit different than we've drawn before. The second ray is going to go through a point that we call the optical center, or the OC. Top of the object, down through the optical center. Where do you think it's going to go after it goes through the optical center? It's just going to keep going straight. So when you put an object a large distance away from a convex or converging lens, you're going to get an image formed on the right-hand side as a result of two solid lines, an image that is smaller, an image that is inverted, and an image that is real. When we had real images for mirrors, they were on the same side of the mirror as the object was on. When we have an image, a real image for lenses, it's going to be on the opposite side. That's because the rays of light go through the lens. They don't go through the mirror. They reflect off of the mirror. Yep. So Kevin's question was, why when it goes from the optical center does it not refract? Well, it does actually. It refracts while it's inside here. But what it does is bends and then bends again. Can't draw it right, but it bends while it's inside, but when it bends back, when it leaves, it ends up going in the same direction that it came from. So there is refraction taking place, and we're approximating that by saying, look, it just goes straight through. The reality is it doesn't go straight through. It bends while it's inside there. Whoops, try that again. It bends while it's inside there, but then bends back in its original direction when it leaves. Does it bend? I'm not sure what you mean. No, it would bend somewhere else. Yeah, it would bend somewhere else. It's going towards the center, but it would kind of bend around the center. And then straight back down the way it was coming from. Except instead of bouncing back, right? Instead of bouncing back like it did on the mirror, it keeps going straight through. Not really straight through, but on the other side, it's as if it went straight through. If we covered up what happened inside the mirror, then that would be perfectly correct. Okay? When we show what's happening inside the mirror, it's not perfectly correct. It's a bit of an approximation, but it doesn't matter because really all we care about is the result, and the result is the same. Okay? Here's what I'd like you to do, guys. Try drawing the next two ray diagrams, just the next two, okay? You get 5 of them. I only want you to draw the next two. When the object is at twice the focal length, when the object is between the focal length and twice the focal length. Let's see what you get for those two ray diagrams tonight. We'll take a look at those tomorrow, okay?